But
Okay.
sir, definitely, I convinced her regarding your profile and your course.
But why did you so? Why did you do so, Salman?
Because sir, you have many qualities, many skills that a student can learn from you, and their skills, no one wants to teach like this, the way you teach, and the way you the skills you have.
Mm-hmm.
No one want to share these skills and these expertise with their students.
Oh, thank you very much, Salman. And I
My
hope
pleasure,
this,
sir.
yeah, you people will get some benefit from this course. And yeah, the Tahura Hadi, can you please introduce yourself? Arusa, welcome to this course. I hope you will enjoy. Okay, Tahura.
Thank you, sir.
Tahura Hadi. Tahura is here?
Hello, Assalamu alaikum.
Walaikum salam. Yes. Can you please
My
introduce
name is
yourself?
Tahura Hadi. Yes, sir. I am Tahura Hadi from KPK, Pakistan. I have recently completed my BS in Physics from Allama Iqbal Open University. Now I am planning to get admission in MS. So I have interest in laser. That's why I joined this class to get some information about laser. So I joined this class to get some information about laser, about the basic of laser and some other topic like application and how to use this in the research work. So that's why I joined this class.
Mm-hmm.
I
Okay.
have no knowledge about laser that much because I have recently completed my BS, so that's why.
So what was your BS project?
And my BS project was gesture car control by hand. We use the sensor MPU 6050.
So, I mean, it was Allama Iqbal University, isn't it?
Yes, sir.
Okay.
Allama Iqbal Open University.
Open University. Okay. Okay. Welcome, Tahura.
Thank you, sir.
Okay. So the thing is that actually, as I mentioned in my first class last time, that this course actually it's more like, you can say, I mean, I don't want to involve too much dry theory of and mathematics, and I want to make it interesting, and also um, because my field is related to development kind of stuff. So in this course, you will see more this kind of things. So as I mentioned, some of the students here are just a beginner in the lasers, and so that is why it's necessary somehow to start from the basics. Okay, so let me start here now. We see one more guy, actually, I want to know about him. Diago. Diago. Hello, Diago. Diago, can you hear me? Diago. Okay, I think, I don't know, he's away or something. Okay, so you people can see, I think, slide which I shared. Yes, sir, we can see.
Yes, sir, I can see.
Okay. So okay, so what you see here, just a minute. Okay. Title, ultrafast lasers, made simple. Okay. So as I mentioned that I will start from the basics and then gradually I will move to ultrafast pulses. You can see some of the animated kind of snaps here, the pictures. And what it shows basically lasers. And why laser fascinates us? Why laser is fascinating to us? Because it is yeah, sure.
Because their applications and the future incoming application about laser.
Yes, application also. And what else?
We talk about the general public. Its color is unique, different from other lights, and it fascinates us so much regarding their light.
Yeah.
I guess its properties like monochromaticity, coherence, and its high power pulses, which are unique from any other light, like ordinary light.
Yeah, sure. There are a number of things. And when first time actually the Mayman, he developed the laser prototype, Ruby laser. And the most of funding at that time he got from the Defense Department. And this laser concept, actually, it's always, if you see the Defense Department, they are too much attracted towards it to make a weapons and this kind of things. Okay, so if you see on the left side of this slide, these web pages, you can visit these web pages, especially the third one, virtuallasergroup.weebly.com. And on this one, you can, I will upload some PDF related to this course and PDF of these slides as well. And also, as I mentioned in the last lecture, you will have recorded lectures as well. Okay, and here, what you see here,
Can I say something?
just a minute. Okay, so probably all of you know about it. The laser stands for light amplification by stimulated emission of radiation. Okay, the laser. And the important thing actually, if you see in this title, light amplification by stimulated emission of radiation, stimulation. The key word in the laser actually is stimulation. Okay, and this stimulation is important. We will see later, slowly, what is this stimulation or what exactly things are going on. But this is just an introductory kind of slides, the first class. And now, all the light emission is spontaneous. Okay, all the light emission is spontaneous. The spontaneous emission is a random emission, and the electrons are jumping from lower to higher to lower randomly. Then the spontaneous emission is always going on. And spontaneous emission, in detail, we see later on. Spontaneous emission actually, basically, it's a key to stimulated emission. If we don't have spontaneous emission, we cannot have stimulated emission. Okay. And it's natural effect, as I mentioned. Okay, so what is stimulated emission actually, if you can see here on this slide, is electron transition that are encouraged by the presence of other photon that is injected externally. Okay. This thing, like what are the energy levels and how it works or something, it will come later on. This is just an introduction kind of things. Okay. So externally, we introduce a photon. Okay. And this photon encourages the stimulated emission. And then we have a lasing action. Probably on the right side, if you see some, these are GIF, you may understand some of the things. Like here, you can see the electron is jumping from higher to lower and some photon are emitting. And here also from lower to higher here. And then photon is introduced externally, and then you have a laser emission. Okay. So who gave this concept first time? So this was the Einstein. Okay, like this kind of stimulated emission is possible. Okay, what he gave concept in a kind of theoretical way a lot, and it took many years to prove that it's really practically it's possible. Okay, so this is just a kind of introduction kind of thing that what are the basic things that are lasers. So if we move further, so you know already that the laser actually basically it's outstanding invention in the sense like it was really fascinating. And if you see before the invention of the laser even, you could see in Hollywood movies, there are they always use a laser weapon, laser pistols. So to amuse the people, and it's always like to fascinate to have this kind of weapons. Now it's reality. I mean, you have a laser weapon and this kind of things. So one of the main thing in a laser is the same direction in the simple words. Okay, so same direction. So lasers actually, it's highly directional. Okay, if a good laser, it's highly directional and it's very intense. So that is why in simple word, we can say that laser produce highly directional and high intensity beam. Okay. And other thing, same phase. People who already study this thing related to laser, any kind of things or some waves, course related to the waves and optics, probably they know this kind of things. But slowly, when I move forward, the beginners may also understand the things when I will explain diagrammatically. Okay, so same phase, monochromatic and coherent. Okay, and third thing here is the same wavelength. Again, it has to be coherent, and spectra is supposed to be narrow, mean single wavelength. Okay, and if you see here this animation, what do you see here? That waves are moving in a phase. Okay, so like here, if you see here, the waves are moving in a phase, trough to trough, crust to crust. Okay, so it means the waves are monochromatic. Okay, and coherent as well. And what is the meaning of spectrum is narrow? Like if you have the spectrum of the laser, like it has to be like this. I don't know how many people know about the spectrum here. Wavelength versus intensity here. Okay, and any of you, if want to ask anything, you can ask, don't wait for the lecture to finish, okay? If you have any confusion or you didn't understand or something, whatever, if you want to ask. Now let's move to the next slide. Coherent. So coherence, actually, this phenomena is very
Sir,
important. Yeah.
Sir, I have a question.
Yeah.
Sir, can we move to first slide?
Yes.
Previous.
Yes.
Sir, here we can see stimulated emission of light. But I studied something like the photon is already present in higher state, and it absorbs the another photon.
Listen. You are Ali?
Yes, Ali.
Yeah, I said, I mean, I'm just showing here some kind of rough GIFs, okay, animations. In detail, this thing will come later on. This is just an introduction, okay? So real one,
Yes,
to draw the energy level and show, that will come later, okay? Okay,
yes,
so
sir.
we'll see later this thing.
Yes, sir. Thank you.
Okay, so here, you to have a rough idea about the coherence. Very important actually in laser to understand the coherence, and in optics as well, or if you study the waves and oscillation kind of stuff. If you see here, this portion, okay, this is spatial and temporal incoherence. Okay, spatial mean in space and temporal mean in time. Okay, so what you see here in first case, okay, in first case, that the waves are not incoherent spatially and temporally. Okay, so if they are not incoherent spatially and temporally, you can see how the different colors, okay, and they are randomly moving. If you move to the second one, this one here, temporal coherence and spatial incoherence. Temporally, the waves are coherent here, and in space, they are not incoherent. Okay, so you can see here. So this is partially coherence, you can say. Okay, but in case of laser, we need to have spatial and temporal coherence both. Okay, and if you move here in the third one, that is spatially coherence and temporally incoherence. Okay, and you can see the different color here, okay, in a space, and you can see temporally it's incoherent. Okay, some waves are broader, some waves are narrow, something like this. And if you move to this portion of the slide, that is spatial and temporal coherence. So spatial and temporal coherence mean all the waves are in phase with each other. Okay, so these are coherent in space and in time as well. Okay, if you see this one, I mean, in a more colorful way, like here you can see if the waves are of the beam or the wave or beam or whatever it is, like a white light coming from the bulb or coming from the tube light or something like this, there's so many colors in it, okay, because they are incoherent. Okay, like this, it's no spatial coherent and no temporal coherence as well. Okay, and if you see on this side here, this is coherent. Okay, so you can see one color only here, and the waves are overlap, face to face, crust to crust, trough to trough. Okay, so these are the things are which are needed in a laser to understand, and I'm not teaching you in a mathematical way yet. This is just showing you that what it could be if it is not coherent and if it is coherent, the waves. Okay, and considering only the wave phenomena. Okay, so the waves here in first three, these diagrams or the figures, you can see they are incoherent in some ways. Okay, and if you go here, then you can see it's spatially and temporally coherence. Okay, so we move now, next slide. Okay, so this diagram you must have seen somewhere, some places. This is a single slit, actually. The light is passing through. I'm not going in detail of this one, okay, this experiment, whatever. I just want to show here the spatial coherent and the temporally coherent, okay. So if the temporally is not coherent here, and you can see different color, but still it is coherent in space, okay, and temporally, but this slit has to be very, very narrow. I mean, comparable with the wavelength of the light. Okay, then we can see this kind of things in general. I mean, this is a case when you introduce incoherent light, like a white light bulb or tube light, whatever it is, and then if you visualize it, something like this, this is a coherent in a space, and this is coherent in a time. Okay, how it is done, this is not a question here at the moment. Wavelength filter, what is wavelength filter? You don't need to go in detail or this kind of thing. I just want to illustrate, I mean, this kind of thing, the coherence. Okay, so next slide. Here, this is also related to the coherence. Okay, the red actually wave here, it has infinite coherence. Okay, time, only consider the temporal time signal, you can say. And the other one, which is a purple one, this is finite coherence. I mean, at certain time it has a coherent, and in the other time it's not. So you can see, like in the beginning here, in the beginning, both the waves are coherent. Okay, infinite one is always there, and finite one also. But slowly, with the passage of time, you can see the finite coherence actually is dragging away from the infinite one. Okay, so this is what happened in actual laser. Actually, you cannot have the coherent radiation always. Okay, even the perfect laser. That is why we need to have some kind of measurements, what we call the coherent length, coherent time, something like this. But later on we'll see what this thing is. But here I just want to illustrate that you can see the infinite coherent and finite coherent, infinite coherence actually, which is ideal case, and it stay coherent, okay, forever. But which is not a, I mean, in real world it's not possible. And the other one actually is finite coherence. Okay, finite, I mean, in the beginning it was, and after a certain time, with the passage of time, it become incoherent. Okay, so this is how you can visualize, or how you can make it like in your brain, how you can imagine in your brain that how it could be. Okay, and now we move to the next slide here. So why do we need the laser? Okay, we need the laser because they are fascinating applications. Okay, so what fascinating applications, you know already, all these people, even layman can know that what laser is doing in these days. You can drill the hole with the laser, and you can engrave, like here you can see it's engraving kind of animation. You can cut the metal as well, and you know that CD drive, DVD drive, they use the laser. Okay, in old time it was a phonograph or phonogram was used, and the needle. So now we use a compact disc, and the laser, it passed through the small holes in the disc, and this laser is detected on the other side of the CD or DVD, whatever. It's a long story how it works, but anyway, this is just an application I'm showing here. Laser, it's very common now in these days as a knife in surgical operation. and it's more precise, you know that. Okay, so another thing which you can see, and it's very important in material science and metallurgical engineering or something like that, cleaning, rust removing. So laser, usually CW laser is used, actually even pulse can also be used in some cases. So here, if you see the last animation, I don't know why it's not working. Anyway, so here, this is the cleaning or rust, removing the rust, the laser. I mean, usually for this kind of purpose, we use the CWM, the carbon dioxide laser is very popular in this kind of. I think there are many more applications. I mean, why do we need laser? I mean, I'm just giving you the kind of introduction here. So if we move to the next slide now. With laser, actually, what can we do? Definitely, there are many things can be done actually. We can have, with the help of laser, we can have when we use in applications, we need to know the power. How intense is laser? What is the power? And if we use a pulse laser, then we need to know the energy or peak power or something like this. And laser actually available in these days, like very, very small, can be a grain size, and to huge, like a large buildings. Diode lasers, semiconductor lasers are very small. And the huge laser, like a chemical lasers or some solid state laser, that huge buildings. So one thing which I mean, it will come later definitely, but I want to mention here, there are two kind of lasers, major category. CW mean continuous wave laser, okay, here. Other one we call pulse laser, okay. And when we call, or when we have the continuous wave laser, the output power usually, we have to measure the output power. So that measurement is usually taken in watts, okay. So it can be kilowatt, it can be a megawatt, or whatever it is, okay, but the basic unit is watts, okay. When we go to the pulse laser, like here you can see, this is animating like the laser pulses are going. In case of pulse laser, that we cannot have, it's not continuous, so we cannot say, okay, this is how much wattage. No, that you can say average power, but average power is not a correct way to measure the pulse laser. So what we do, we actually measure peak power, because why peak power? There is a reason. Like if it is a form of pulses like this, like this, like this, okay. So what is the power at this peak? What is the power at this peak? What is the power at this peak? Okay. So CW is simple like this, okay. We can measure the power, no problem. But if you have like this pulses, and if these pulses are like this, and you cannot apply this rule, that what we say peak power, okay. We'll see later on this detail and the peak power. So we measure the peak power, I mean, how many wattage or whatever it is, and also energy, okay. So energy, what is energy? I mean, what these are units, I will come later on actually. You don't need to panic and don't need to feel like you don't know or something like that. This is just introduction kind of things, okay. So pulse energy up to 7 to 17 joules are possible to now, okay, and up to 10 to 20 watts, okay. And this frequency here, This probably, I mean, too early to tell you about the frequency. This frequency is linked with something. I mean, when we operate the laser, so it has a certain repetition rate. Okay. So I will skip this thing, and when the real portion will come, then I will tell you about this frequency. Okay, so these are some units you can see, which you need to know here, that it's 10 to 3 kilo, mega 10 to 6, giga is 10 to 9, and tera 10 to 15. The terawatt, when we call terawatt laser in a pulse laser is very important and very famous in these days. And petawatt also. Petawatt, very few facilities in the world who can have petawatt. Petawatt, these are peta and watt. If I say peta watt, it means I'm saying about the peak power. Okay. Exa watt, it's a peak power. Okay. Don't get confused. I mean, this thing will come later. Okay. Let's move to the next slide. Okay. With the laser, I mean, as I mentioned, we can do many things. Okay. And laser can be produced in a different kind of mediums. Okay. So medium, just a minute, sorry. Okay, so here if you see, laser action is demonstrated, means the medium from where the laser is generated. Okay, so laser action can be generated in gases. So there are gas lasers. It can be in liquids. So it's called it doesn't call the liquid laser, but other name is given like a dye laser or something like that. And solid materials. Solid materials means the laser medium is solid, like you will see later on that anti-yag, titanium sapphire, and anti-glass or something like this. And semiconductor material you will also see. So also some other materials in chemicals, in fiber optics. So laser action is possible in gases, liquids, solids, semiconductors, this kind of materials. Okay. And lasers, because of the gain medium, if you have a gas, wavelength will be different. For the liquid, different wavelength will be emitted. Solids, different wavelength will be emitted. Semiconductor case will also be, I mean, it will emit the different wavelength of the laser. Okay. And if you see here, the green one, just a minute. Okay, so there's some of the animation that is not working. I don't know why. Okay, so time is okay. After this, probably I will share another link. Okay, so we will have session again for a few minutes, like having a break of 5 minutes or something like this. Okay, now I have 10 minutes. Okay, so what I don't understand, some of the animations are not working here, which is quite irritating to me. Anyway, we keep moving. Okay, so as I mentioned in the last slide, the laser is categorized pulse laser and continuous CW lasers. Okay, so this is a pulse laser here, and this is a continuous laser. You can see the beam is coming continuously. And if we have pulse laser mean that the duration of the pulse can be millisecond, can be microsecond, can be nanosecond. Okay, so In this way, if you see here, like as short as, there is something actually which I don't understand anyway. Okay, so femtosecond means 10 raised to the power minus 15 second. So the laser pulse appear only for 10 to the power minus 15 seconds. Okay, so it's a very, very short interval of time. And it can be a picosecond, which is less shorter. It can be a nanosecond, which is less shorter. You will see in the next slide. Okay. Please mute your mic because I hear some noise. Okay, so
Ali Hassan's mic.
okay, so output power, as I mentioned in the last slide, it may vary from microwatts to petawatt. Okay, petawatt 10 to 15, and femtosecond 10 to minus 15. Okay, so we can have a shorter pulse like a femtosecond, or even shorter than this one, which you call the attosecond as well. And we can have peak power up to petawatt. Hexawatt, they're also trying, but petawatt is the maximum at the moment. Okay. Okay, so last thing which is on this slide, what is mentioned is laser is successful offspring of a marriage between optics and electronics. So whenever I teach laser somewhere, wherever in the university or whatever, I always insist students, if you want to learn the laser, or if you want to do something in the laser, in the field of laser, then you have to understand the electronics. Okay. Quantum electronics is also a laser. Okay. And so if you see later on, you will see later on that why I'm calling it a marriage between the optics and electronics. Whenever you build the laser, I mean, there are many things which are linked with the electronics. And basic building block of the laser is a feedback system, which we also study in electronics. Okay, so the laser actually is offspring. Okay, it's a child of a marriage couple, and one of the couple, I mean, is optics, and other of the couple is electronics. Okay, so this is very important to keep remember. And now we move to the next slide. Okay, you need to know a little bit about the history. This journey started from, you can see it's 1970. Okay, Einstein predicted the possibility of stimulated emission mathematically. And Rudolf Landenberg, actually, in 1928, he confirmed that the existence of the phenomena, the stimulated emission. And after all, I mean, after that, if you, in 1939, Valentin Fabricant, actually, so he predicted what the stimulated emission to amplify the short waves, microwaves. Okay, so at that time, in the beginning, the people, they didn't know about the light. In the light, the stimulated emission can be in the visible region. Okay, so like Einstein gave this concept in 1917, then 1928, Rudolf confirmed this one, and then Valentin after that, we can amplify the short waves, and then Willis in 1947, he made the first demonstration of this stimulated emission, but not in an optical frequency or a wavelength range. Okay, and 1950 actually, Alfred Kessler, okay, he introduced or proposed the concept of optical pumping. Before here, 1947, Lamb, I mean, they didn't use the optical pumping concept. Okay, so in 1950, actually, this optical pumping concept was proposed. Okay, so a brief kind of history. I'm not going in detail, and further, I mean, in the next slide, you will see some. Here also you can see the history, but in this history, major thing is covered is maser. What is maser? Anybody knows what is maser?
It's microwave
Yes, sir.
amplification by stimulated emission of radiation.
Yes, David. Yeah. So after 1947, actually, the people, they start working on this maser, microwave, short wave, to amplify and to have a stimulated emission. And C.H. Town, Gordon, Zeiger, Basov, and the different scientists, they start working 1952 and 1954, actually. The first practical maser they invented. And if you go further here, 1958, Towns and Schwalow, Basov, actually, they were working on the kind of optical pumping and optical amplification. I mean, not in a microwave range, but in optical visible range, kind of, you can say. So in 1952, Towns, actually, I mean, a very important person in this kind of, I think, won a Nobel Prize as well. So it's 1 minute left. Okay, I stop now, and after 5 minutes, I will send you the link again. Okay, understood?
Sir, you are muted. Sir, we cannot hear you. You are muted.
Yeah, now. So what I'm saying, I'm leaving now, and I will rejoin. I will send you the link after 5 minutes. Okay. So all of you stay here and join again. Okay. This is a time limitation of this software. Okay. Now see you again then after a while. Okay.